Welcome to the seminar of COSIC. Today we have a guest, Claudia Bartoli from IMDEA in Spain. She's doing a PhD with Ignacio Cascudo, and today she's going to talk about Sigma protocols and black box secret sharing schemes for us. So, thank you.
Well, hi everyone. Thank you so much for inviting us today. So as Emma said, I'll be speaking on our recent work that we published this year at PKC, which is entitled on Sigma protocols and black box secret sharing schemes. So I'll start by a bit with some motivation of how we started with this work. So let me briefly introduce Sigma protocols. They are these very well-known free-run protocols in which a prover wants to convince a verifier that she knows some secret without revealing any information about it. Of course, this protocol must satisfy these three properties that are completeness, case special soundness, and honest verifier zero knowledge. So one of the most famous Sigma protocols is the Schnorr protocol, in which a prover wants to convince the verifier that she knows the discrete log of some known value h. So in this case, she would know w, which would be g to the w. Where G is the generator of some group capital G of prime order Q. So in this case, the protocol works as follows. The first step is just committing some randomness. So in this case, the random would be raw. And the commitment is A. This is what it sent as first message. The second message is what we call a challenge, which is simply some random value selected from, you can see my pointer, yeah. By the way, you can interrupt me anytime if you have questions or doubts about the slides. So I was saying C is the challenge. That is this random value selecting from here, from that queue. And the last message is a linear combination of the witness, this challenge, and the randomness committed at the first step. Finally, the verifier just checks this equality. And if the equality passes, then is convinced that the prover knows the secret. So this protocol satisfies the three properties. In particular, it satisfies the two special soundness. And this is, well, because if we have two different conversations that are valid, having the same first message, then what we can do is, well, basically, because they are valid conversations, they satisfy the equality. And if we divide them, we have this equality here. And now if we divide C minus C prime here, we get G to the Z minus Z prime over C minus C prime, which is a witness. So this is how we extract it. And this works because C minus C prime, in this case, is invertible. And this is the case because here we are assuming that we are in a cyclic group of prime order, and in particular that the challenge is selected from a field. So we ask ourselves, what happens if we're not in this scenario? So what happens if we maybe don't know the order of the group, or maybe the group is just not prime and it's not as easy? So one solution is like nice and well, naive, is just to, well, say we can select binary elements. So we can have a challenge that is just 0, 1. And this satisfies the property and has two special soundness. But of course, what it has is a soundness error of 1/2, because you just can guess with 1/2 probability the challenge. So what is usually done in this case, in order to have a smaller soundness error, is just to repeat this protocol lambda times. At the end, you get a protocol that has soundness error 2 to the minus lambda. But of course, like, the efficiency of the communication is not as good as we would like. So the goal of our work is, well, to design a Sigma protocol that can prove preimages of homomorphisms that can work over any abelian group. And we do this using the fact that Sigma protocols can be described through linear secret sharing schemes. So let me briefly introduce linear secret sharing schemes. There are these protocols that allow you to share some secrets among n participants. And in particular, when we consider the linear secret sharing schemes, the sharing is given by the multiplication of some matrix that we usually call a generator matrix. And in particular, they have the properties that they have T reconstruction, in the sense that if any T participants put together the shares, they learn no information about the secrets. And they also have R reconstruction, in the sense that any R participants, if they put together the shares, they always are able to reconstruct the secrets. So an example of how the Sigma protocols can be described through linear secret sharing schemes is the case of Schnorr that we just saw at the beginning, using Shamir secret sharing scheme. So in this case, we can consider the case of Shamir secret sharing scheme for one secret, and with two reconstruction. So this is given by this polynomial here, where W is the secret and R is some randomness. So the protocol would work as follows. So the first part is just the same as before. We commit to some randomness. That is actually the random value that we'll use in the Shamir secret sharing scheme. Then the challenge can be seen as a random selection of a participant. This can be thought somehow some kind of linear secret sharing scheme in the head or something like that. And the last message would be to share the corresponding share to that participant. So in this case, is an evaluation of the polynomial, and this is what we send as last message. So more in general, we in our work, we describe these two general Sigma protocols and with general linear secret sharing schemes. So let's assume that we have a linear secret sharing scheme that has T privacy, R reconstruction, and provides shares for N participants. Because it's linear, we can write this as a matrix M times the secrets and some randomness. This provides the shares. And in particular, for participants, let's say I, we call Mi as the rows determine the shares of that participant. So the protocol is the following. The first message is now the commitment of the randomness, again, used in the linear secret sharing scheme. And it's committed using the F, which is the homomorphism for which we are proving knowledge of the preimages. Okay, so this is a statement that the prover knows that the Wi such that xi, which are the public values, is equal to fwi. Now again, the second message, which is the challenge, again is like the selection of a random participant. And the last message is the share corresponding to that participant. So in this case would be the Mi times the secrets and the randomness. And this is what is sent. So this protocol satisfies the three properties. The first one, completeness, is given by the fact that F is an homomorphism and that the secret sharing scheme is linear. So here in this equality, everything works because are just linear multiplications. Then it has R special soundness, where R is the reconstruction parameter, because of course we are sending shares in the last message. So if we send R different shares, then we can reconstruct the secrets. And it has R minus 1 over N soundness error, where N is the number of participants. And finally, satisfies owner verified zero knowledge because of the privacy of the secret sharing scheme. So because we are just sending one share, this provides privacy. And moreover, the communication of this protocol is given by the size of the shares, because we are sending shares, so the bigger the shares are, the more communication that we have. So just recall that the goal of this work was to have a Sigma protocol that provide proofs of plain text, proof of preimages of homomorphisms defined over any abelian groups. So let's think what we want from the secret sharing schemes in order to have that Sigma protocol that we wanted. So the first thing is, of course, that we want the secret sharing scheme to be linear, because as I said, this provides the completeness property. Then we want to have one privacy and two reconstruction, because that provides two special soundness, because we can reconstruct from two shares. We would like to have a large number of participants, because in that way we have a smaller soundness error. We would like to have a small share size because of the communication that I said before. And we would like it to be defined, or that can be applied over any abelian group. And because of that, what we use are black box secret sharing schemes. There are these schemes that were introduced by Desmel and Frankel 94. And there are basically linear secret sharing schemes that, in fact, can be applied over any abelian group, obliviously to its structure. And moreover, for this case of black box secret sharing schemes, we know that the share size is bounded by log n. This is a result from Kramer and Fer in 2002. Okay, so let's see how black box secret sharing schemes can be constructed. So let's assume we have a family of matrices, we call this M, from M1 to Mn. There are matrices defined over the integers. And now for each participant I, we define shares this way. So we multiply the matrix Mi times the secrets plus some randomness. Okay, this is easy. And because we want to have two reconstruction, we ask to this family to have the following property. So we would like that any different participants, so I different from J, satisfy the property that the subtraction of their matrices has a pseudo-inverse. Because this way, if we subtract the matrices, the shares that are defined this way, if we multiply then the pseudo-inverse, we get the secrets. So how do we get such a family of matrices? So here are some examples. So you can see for the case of k equal 2, so for sharing just two secrets, we have here a family of 4 matrices that satisfy this property. And this gives us a black box secret sharing scheme that shares 2 secrets among 4 participants with a share size of 2 elements, which is optimal, right? Because it was log n. And more interestingly, for the case of k equal 3, we have a family of 8 matrices that again satisfy this property, that any difference of these two has a pseudo-inverse, and defines a black box secret sharing scheme for 8 participants sharing 3 secrets with share size 3. So we would like just to keep going and have a huge family of matrices that satisfy these properties and that have this minimum share size. However, it's not true in general that this happens, and it's actually hard to find a bigger family in this way. So we need to find a different way to construct a family of matrices satisfying these properties that is actually larger, because, as I said at the beginning, one of the properties that we wanted from the secret sharing scheme is that it has a large number of participants. So we came up with a construction of these black box secret sharing schemes that is based on a previous construction presenting the work of Kramer and Damgaard in Crypto 2009. And it works as follows. So first, we'll consider the family that I just showed of 8 matrices of size 3 times 3 that already satisfies the pseudo-inverse property. Okay, now we want to extend this to some n that we'll say is a to some m. Okay, so we extend the number of participants. So if we do this, now we can identify each participant I in n as a vector, like a uniquely determined vector in base 8. So each I would be something like I0, comma, im2 minus 1. And this has a unique correspondence to the matrices in this family here, n. So now what we do is that for each participant I, we construct a bigger matrix that we call Mi, in which we put in the columns the matrices ni0 until nim minus 1, and then we add zeros, and then we switch one position down each time. We get something like this. And we do this for every participant. So if we take now a different participant J, we can do the same reasoning. And because this is a unique identification, we can always assume that we know that there's at least one element that is different from this identification, right? So we can assume that is the first one. So let's say that we have that ni0 is different from nj0. So if we subtract them now, what we get is that in this diagonal, we get the differences of these matrices. And these matrices are non-zero. Like this subtraction is non-zero because we are assuming that they are different. And because of that, since these matrices belong to this family N, and they satisfy the pseudo-inverse, from here we can construct a bigger pseudo-inverse for this subtraction here. So these are not like, it's not a detailed description on how we do it, but at least I hope you get an idea of how this is done. But we end up, as I say, with a bigger family of matrices that also satisfy the pseudo-inverse property. I don't know if you have any questions so far. Okay, well, anyway, the main idea is that we manage to get a family of n matrices for any n that satisfy the property of the pseudo-inverse, and therefore we can describe a black box secret sharing scheme from them. So in particular, what we get is a black box secret sharing scheme that shares k secrets and that has 1 privacy, 2 reconstruction, and the share size are given by k plus lambda minus 3, where lambda is this parameter here. So we're assuming that the number of participants is 2 to the lambda. Right, so now we can use this black box secret sharing scheme to describe a Sigma protocol. That was what we wanted from the beginning. So the protocol is more or less as I described before, but the only difference is now that we are using a concrete secret sharing scheme. That is this black box secret sharing scheme that I just described, with 1 privacy, 2 reconstruction, and 2 to the lambda participants. So the first message would be just as always. The second message, again, is the selection of some random participant. And the third message is the share corresponding to that participant I. So at the end, what we get is a Sigma protocol that has 2 special soundness because of the property of the black box secret sharing scheme, a soundness error of 2 to the lambda, and a communication complexity of k plus lambda minus 3. And of course, because we're using black box secret sharing schemes and they had this property of the pseudo-inverse, they can be used for any abelian group, despite of the order, even if the order is unknown or is not prime, wherever it can be used. So this is the main construction of our work. And now let's see some applications that it may have. So the first application that came to our mind is in the realm of class groups, and in particular, the framework described by Castaños and Laguilhem in 2015. Because here they consider a group of unknown order in which they have a subgroup for which the discrete log is easy to compute. However, they are dealing with groups of unknown order, so there is not trivial to do Sigma protocols. And in particular, there are 2 homomorphisms that we could use or for which we could apply our Sigma protocol. The first one is just discrete logarithm. And the second one is a proof of plain text for the encryption scheme that they defined. And now if we compare this with different works, in particular for the case of discrete log, what we get is, well, first, the first work that we have here, Castaños et al. In Crypto 19, they have larger communication than us, because what they do is what I explained at the beginning. They consider a binary challenge and they repeat the protocol lambda times. Then they improve the communication in a work presented at PKC 2020. However, they need some assumptions, in particular the strong root assumption, which implies that the selection of G, which is the generator of the group, is randomly selected, which is not always the case. And more recently, there's the work of Brown et al. At Crypto 2023, in which they don't use that assumptions, they define a new assumption. However, in that case, then they don't have knowledge because they don't extract the witness. So it's a bit different. And in that case, they don't need the extraction, and they came up with this solution. So what we have here is that our work is, has better communication than the first one, and compared to the other two is not much worse. but it doesn't rely on any extra assumptions. Plus, it has extraction, so it's a proof of knowledge. And some other applications. Well, we saw that our construction could be generalized to decay-ready functions. There are functions that were defined by Kramer and Abgar in their work of Crypto 2009. And then basically functions that are almost homomorphic. And we explain in the paper how they can be adapted. And one example of these decay-ready functions is the Joye-Libert encryption function that is described here, right? So we take a message U, a randomness S, and this is the encryption is given by G to the U times S power to 2 to the L. So because our protocol can be adapted to the decay-ready functions, we can apply directly our black box secret sharing scheme to have a sigma protocol for this case that has two special soundness of 2 to the lambda, and again has a communication complexity of k plus lambda minus 3. That was the same that we had before. However, in this case, we know how to improve it for the case of Joye-Libert. And in particular, I don't want to go to the details, but just to give you an idea, we use extensions to Galois rings. This is something that is not new, has already been done, for example, in the work of Atematol at TCC 22. And basically, the idea is that we can extend the ring Z2 to the L to the Galois ring, which is a ring of polynomials. But the nice thing here is that this ring of polynomials have the following property. So we can define what is called an exceptional set that we call omega. And this is a set of polynomials of degree d minus 1. Well, I didn't say, but well, the Galois ring is defined like this, and Fy is a polynomial of degree d. That's why here is d minus 1, and this is also the degree of the extension. But anyway, in this exceptional set, what we have is a set of polynomials of degree d minus 1 where the coefficients are 0 or 1. And they have this nice property that if you take any two different values from here, from omega, the subtraction of them is invertible. So this is actually perfect because if you remember what we had at the beginning, we would like to have like the difference of challenges be invertible so that we can do the trick. So what we can do is take this ring, go to the Galois ring, and then apply Shamir secret sharing scheme there because they have this property, and then I use this as the linear secret sharing scheme for described in the sigma protocol. So in this case, we have a sigma protocol that, as you see here, it has better communication complexity because now you only have k elements. So you're proving knowledge of k preimages, and you just share as a last message k elements and no longer k plus lambda minus 3. That was the case before. And just to conclude, it was quite early anyway, what we did in this work is, well, first we formalized the sigma protocol's description through linear secret sharing schemes for any linear secret sharing scheme, and we include the non-interactive versions. We generalize a construction of sigma protocols using black box secret sharing schemes so that it can be applied to any abelian group. We show the applications of over class groups, and we define the extension of the sigma protocol over decay-ready functions, and for the specific case of Joye-Libert, we improve the construction using, as I just explained, the extensions to Galois rings and the Shamir secret sharing schemes there. That concludes my presentation. Thank you so much.